Okay, so first graph here, we have a graph of book thickness. On the x-axis, we have the number of sheets or pages in the book. Okay, and then on the y-axis, we have the thickness of the book in millimeters. Obviously, the thickness of the book responds to the number of pages it has. Okay, so the number of pages or sheets is the manipulated variable and goes on the x-axis, and the thickness of the book being measured, okay, is on the y-axis. All right, so we want to calculate a couple of things here. All right, we want to calculate the number of sheets in a book that is 80 millimeters thick. Okay, whenever you are given a graph that looks like this, and I don't mean that it's about book thickness and number of sheets. I mean it's a linear graph, and it has the equation for the graph. Use the equation. Okay? It would not give you that piece of information if it wasn't meant to be used. So we are definitely wanting to use y equals m times x plus b, which for this graph is 0.15. Okay? And what are the units for that slope? I almost did the doctor. Millimeters per sheet. Okay? So the slope of this line is telling us the thickness of one individual page in the book. Okay? That's why it can help us to figure out how many pages are in a book of a given thickness, or what the thickness of a book of a given number of pages would be, either one. We can find either y or x. So this first question, what am I being asked to find? Y or x? Right. Okay? I'm being asked to calculate x because they gave me what's on the y-axis, the thickness. Okay? So that's what I have to look at when I'm trying to solve an equation or solve a problem about a graph. What did they give me? And what does my equation give me? That was the first thing I asked you. What does the slope of this graph represent? Because every graph's slope represents something different. They all represent change in y over change in x. But what's on the y and x is always different. In this case, it's thickness in millimeters and sheets, okay, or pages. Right? So we're getting millimeters per page or millimeters per sheet. So if I want to calculate the number of sheets that's in a book that's 80 millimeters thick, as you guys just said, I am looking for x because number of sheets is on the x and millimeters is on the y. So they told me what y is, and I'm trying to solve for x. All right, manipulation. The 3 rules of algebra. If I want to move something, I do the opposite. What I do to one side, do to the other. The golden rule of algebra. Okay, and I move what's not attached first. Okay, I'm looking for x. In that equation, what's not attached to x? B. Okay, b is not attached. Right now, I'm adding b. So if I want to move b, I need to subtract. Okay, positive b minus b is 0. b is gone. Okay, but what I do to one side, I have to do to the other. Y minus b equals m times x. All right, all that's left is attached to x. Okay, that's m. So how do I move m to the other side? Right, because I'm multiplying by it right now. So I'm going to divide. M divided by m is 1. Okay, it's important. If it's 0, 0 times x is 0. I don't want that. Okay, 1 times x is x. See how this works? Okay, by dividing m by itself, I get rid of it by making it 1. And then when I multiply anything by 1, it's itself. Okay, so it cancels off. All right, but what I do to that side, I have to do to the other, and now I'm solving for x. All I have to do is plug in my numbers.
Would we get docked marks if we don't do that, but we do it like with the numbers in it? Like
You will not get docked marks, okay, if you manipulate it with the numbers already in.
Okay.
Yeah, manipulation is manipulation. I always find it's easier to manipulate before the numbers are in. But if it's not for you, do it whatever best for you. Okay? All right. So when I plug in my numbers, this was going to be, was it 80? 80, yeah. So 80 minus, what was B? B was 5. Okay, divided by 0.15. Now, before we do this, what does the y-intercept represent on this graph?
How thick no pages.
How thick a book with no pages is. In other words, the thickness of the cover. Okay, that's a little bit more like intuitive, right? Or maybe counterintuitive. Okay, but you have to think about that one a little bit more. Okay, it's always important to know what M and B represent on the graph. All right, so I got 80 minus 5, so I got 75 divided by 0.15. All right, that book has 500 pages. How important is it for me to write pages beside that? Very. Yeah, gotta have units on that. All right. Question number 2 is a little easier. I want you to calculate the thickness of an 805-page book using this graph. Give you a minute on that one. All right, well, let's look at this next one here. Okay, so they're asking us to calculate the thickness of a book that has 805 pages. So what are they asking us to calculate, y or x? Y, okay, because thickness is on the y-axis. Okay, so y equals 0.15 millimeters per sheet times 805 sheets, okay, and plus the 5 millimeters for the cover. Okay, so 0.15 times 805, okay, plus the cover. All right, it'll be 125.75 millimeters thick. In other words, just under 13 centimeters. Okay. Sorry, I should write it as it actually is. 125.75 millimeters. There's not 2 decimals in that number. It's not an IP address. All right. And number 3, we already talked about. It was the first thing we talked about. How many millimeters per sheet? That's being told to us by what part of the equation? By M, right, by the slope. Okay, the slope is millimeters per sheet. Okay, everybody all right with that one? All right. Okay. So I've got a position versus time graph. Sorry, I built it kind of hastily this morning, so it's not labeled. Shame on me. All right, so we got position in meters. Okay, on the y-axis, we got time on the x-axis. Okay, so position versus time graph, we have the equation for both runs. Okay. What's the velocity for run 1? If you're writing stuff down, you're doing it wrong. This would be a 1-mark question. .26 meters per second. Okay, how did I figure that out? Okay, I did exactly what we did on the last graph. When I asked you, what does the slope represent on this graph? And you guys all went, oh, millimeters per sheet. It's the thickness of 1 sheet of paper. Okay, I did exactly the same thing here, right? What's the velocity of the object? Okay, well, this graph has position in meters and time in seconds, and velocity is change in position over time. So change in positions on the y, change in time is on the x. When I divide those, I'm calculating the slope. Okay, Okay, just look at your units. The units for velocity are meters over seconds. That's y over x, which is exactly how you calculate slope. Y over x. Okay, you can analyze any graph that very same way. Okay, one of the first things you should do if you encounter a graph is figure out what does everything represent on this graph. Okay, here's another one. What's the initial position of the object? .195 meters. Okay, it's the y-intercept. It's b. Okay, why is it b? Well, b is where the object is at time 0. Okay, everybody all right with that idea? Okay, these are like 1-mark questions. They could be a multiple choice question on a test. Okay, or in a written response, they would actually be 1 in brackets beside the question. All right. I want you to calculate the final position of each object after 20 seconds. Okay, calculate the final position of both objects after 20 seconds. Oh.
So
There, some way to do it. I'm saying velocity because velocity is the truest description of this, because it's position divided by time. Speed is distance over time, which they could be mathematically equal, but they're not the same thing, if that makes sense. So it's possible if I asked you to calculate the average speed, you'd still go final position minus initial position over time and get the same number, but you wouldn't put a direction on it. Whereas for velocity, you'd say positive 0.26.
okay.
Yeah? Okay, so 20 seconds. Calculate the final position after 20 seconds. You have more than 20 seconds to do that, just in case there's any confusion. Okay. Everybody ready to go over that one? Oh, I left it running. Oh well, there'll be a bit of dead time in the middle of that video. Okay, so we need to calculate the final position. So am I calculating y or x? Y, because position is on the y-axis. All right, so I'm solving for y, and I gave you the x value. I told you after 20 seconds. So that means that for the blue one, so I'll use blue, so we don't get confused. Okay, so for the blue one, y will equal 0.26 meters per second times 20 seconds plus the initial position of 0.195 meters. Whoops, I won't put the m on there yet. Okay. All right, so really what we're doing here is we're going velocity times time, which gives us distance or displacement, plus the initial position, final position, okay? So we're calculating final position there. All right, 26 times, sorry, not 26.26 times 20 plus 0.195. All right, so the final position after 20 seconds for run 1 will be 5.4 meters, positive 5.4 meters. Okay. And then for our second run, it's the same calculation. We're still calculating y, but we use different numbers. We use a speed or a velocity of 0.38 meters per second times 20 seconds plus the initial position of 0.115 meters. 0.38 times 20 plus 0.115. All right, so we're getting 7.7 meters, positive 7.7 meters. And that makes sense. If I look at this graph, run 2 faster or slower than run 1? Faster. Okay, it's a steeper line. Its slope is greater. It's going faster. Okay, so it should go further. Everybody all right with that? All right. Now, I want you to calculate how long it will take each run to reach a position of 65 meters. Okay, so we're trying to find how long to reach 60 meters. And I'm going to pause it. Okay, so we are looking for how long it will take. Are we looking for y or x? X. Okay, so that means we have to manipulate y equals m times x plus b to solve for x. So we move b first by subtracting b from both sides. Y minus b equals m times x. Divide both sides by m, and we've got our formula for x. Okay, so for run 1, we said that the final position was going to be 65 meters minus our initial position, 0.195, divided by m, 0.26. All right, so for run 1, we are looking at 65 minus 0.195, okay, divided by, what was the slope for that one again? 0.26. All right, so we're looking at 249.25 seconds. Okay, if you didn't get that answer, but you did everything like I did, you didn't quite do everything like I did, okay? If you punch this into your calculator, 65 minus 0.195 divided by 0.26 all in one step, you do not get this answer because your calculator will do order of operations, and it will do the division first, and then it will subtract that number from 65, which does not give you the correct answer. So you have to do the top divided by the bottom, and then you will get the right answer. Okay, you have to outsmart your calculator. All right, and then for the second one, again, we're looking for how long it will take. 65 minus 0.115 divided by 0.38. Okay, so again, 65 minus 0.115. I hit enter to separate it. Now I can divide by the slope. Right, I get that that will, the final position of that one, or sorry, the length of time for that one is 170.75 seconds. And that makes sense. It should take less time. It's going faster. All right, everybody okay with that? That might be really helpful for your lab, given that it was position versus time graph. Okay, let's question.
My calculator is just giving me the absolutely wrong answers.
Okay, let's have a look here. All right, this is a velocity versus time. I'm going to have a look here in just a second. Let's we've got two different runs on there, two different cars. I want you to calculate for me the total displacement for each one for the first 1.25 seconds. Okay, so I'm looking for what is the total displacement for both to 1.25 seconds. See if you remember how to do that from the other day. Let's go over this one. I think people thought they knew what they were doing, and they might be wrong. So, if I want to calculate total displacement, I want to take average velocity and multiply by time. But the velocity is changing for these objects. Okay? They are accelerating, because this is a velocity versus time graph that is showing their velocity changing. Everybody with me there? Okay. So, what I have to do for an accelerating object, if I want to calculate how far it's going to go, is I need to calculate how far it will go if it doesn't accelerate. That would be this right here, its initial velocity, the height, times the time, the base. Okay, and then I need to calculate how far it will go while it's accelerating. That would be the triangle above it. Okay, that will tell me how far it's going to go while accelerating. And then I would add the two numbers together. Okay, so what I need to know is how tall the rectangle is. Do I have that?
Yes.
Yes, the rectangle for the blue line is 0.319 meters per second tall. Okay, and its base is 1.25 seconds. Now, that calculates how far the object would have traveled if it traveled at a constant velocity of 0.319, but that's how far it would have gone. Okay, now I need to add on to that how far it goes as a result of speeding up. Okay, and that's the triangle above it. Okay, so the base of that triangle is still 1.25, but I do not know yet how tall the triangle is. So I need to calculate that. So what do I need in order to figure out the height of this triangle? I need to know what y is at 1.25 seconds. Okay? If I'm going to calculate how tall this triangle is, I need to know where the line is at this point in time. So that means, what is y, okay, when x, so 0.612, is 1.25 seconds. Okay? I'm not going to add on the y-intercept. I'm not going to add on 0.319. Why not? Okay? If I add on 0.319, I'm calculating this whole thing. I only want to know this part right here. Does everybody follow me on that? Okay. Okay, so my triangle is 0.07, sorry, I put in the wrong number there. 0.612 times 1.25, not 0.125. Okay, 0.765 meters per second tall. Okay, now, I'm calculating the area of this triangle because the area of this triangle, okay, will be average velocity times time. Base times height divided by 2. My velocity changes by this much, but my average is halfway in between. Okay, so what I need to do there is just simply go 1.25 times 0.765 over 2. Okay, and then for this, it'll be 1.25 times 0.319. Okay, so average velocity times time plus average velocity times time. Okay, so this is 0.478 meters. And then the bottom one, oops, 0.319 we said, right? Two decimal places. That's fine. Okay, so we're going to take, 0.39399. Okay, if I add those two numbers together, okay, 0.478 and 0.399, I will have the total displacement of the object. So plus. Okay, so the total displacement's 0.88 meters. All right, do that for the red one. I'll leave all my work up there. Okay, do it for the red one. Okay, we had to calculate what y is at 1.25 seconds. Okay, and we had to draw in essentially the rectangle and the triangle, okay, that we were going to have to calculate the area of. Okay, so once again, I want to calculate average velocity times time, but I need to do that for essentially two different sections. How far the object would travel if it didn't accelerate, that's the rectangle. Okay, and how far it goes while it's accelerating, that's the triangle. Okay, those two parts are we treat them separately even though they kind of happen at the same time. Okay, so the first thing I need to do is calculate what is y at 1.25 seconds. It's not exactly 2.0, but it's going to be close. Okay, but I still need to calculate what it is. Okay, now I only want the height of the triangle. When I calculate y, I'm going 1.25 times 1.25, oddly enough, because the slope and time are the same. Sorry, I didn't realize that when I picked that number. Okay, so times 1.25 plus 0.438. Now, I'm not going to add the 0.438. Why not? Well, that's the height from here. I only want the height from here. I don't need the whole thing, so I'm not going to bother adding on that point. That's the height of the rectangle. I only want the height of the triangle. Okay, so I'm going to get the height of the triangle by kind of avoiding that step. Okay, that'll get me the height of the triangle. So 0.125, so we're looking at 6.25? No. 1.25 times 1.25. Sorry, 1.56. What was I thinking? Okay, anyway, 1.56 is the height of my triangle. Okay, the base of my triangle is 1.25 seconds. And I've got my rectangle that has a height of 0.438 and a base of 1.25 seconds. Okay, so now I can calculate the displacement here, and add the two together. All right, so I'm going to have my 0.438 times 1.25. That's base times height for the rectangle. So there's the displacement in the rectangle. And I'm going to add that to the displacement I get for the other part, which will be the base, 1.25, times the height, 1.56, divided by 2. All right, so there's the area of the triangle. So now when I add that to that number, there's my total displacement. Okay, listen up here, guys. Okay, listen, it's not always going to be that complicated. Okay, sometimes you're just going to get a graph that's got random shapes, and you just got to figure out all the triangles and all the rectangles. You're not going to have to use y equals mx plus b. Okay, but if you get a linear graph, then this is the way you'll have to do it. Okay, but if you got a velocity versus time graph that looks a little different than that, then it's a little bit easier. Even if it's more shapes, it ends up being easier to do because the calculations you do are a little more obvious or straightforward. Okay. All right. Okay, so this is also very much like your lab that you did yesterday. Except this is data from a lab where we actually put the stickers down on the floor. Okay? No, sorry, it wasn't where we put stickers down on the floor, but I sampled it much less, so it wasn't 20 times per second. Okay? You can see here that we don't have nearly that many data points on here. So, what I would like you to do with this position versus time graph is show me what the velocity is for run number 4. It's just 6, yeah. Okay, it's just 6. This is a position versus time graph. Okay, and a position versus time graph has meters on the y-axis, seconds on the x-axis. Change in y is displacement. Change in x is time. Displacement over time is velocity. Velocity is 6. Okay, because the slope of the line is representing change in position divided by change in time. Okay. Now, what if I was manipulating run 2 so that I showed what the slope equaled? Okay, what would that look like? All right, so run number 2 has this equation. Y equals 2.4 times x plus 0.0333. All right, which one of those numbers is the slope? 0.2 or 2.4. All right, so I want to manipulate this equation so that I'm solving for 2.4. So it'll end up that it's 2.4 equals something. Okay, but I'm not putting in any numbers. Okay, I'm just manipulating this in the same way I'd manipulate this. Okay, if I manipulate this for m, I subtract b, divide by x, that equals m. Doing the same thing with that equation. Just there's numbers in for m and b. Right? Does it really change anything?
No.
Not really. Okay, it's just going to look like this. M, which is in meters per second, equals, okay, y minus 0.0333 meters divided by x. Okay, it's the same manipulation. Right? I've solved for m. That's how I would calculate m with any y or x value.
So is that what we do on
I'm not going to answer that question. Okay. All right. Now, because I can read your mind better. All right. We have, it says displacement here, but this is a position versus time graph. So this one doesn't involve using y equals mx plus b. This is more like what was on your quiz today. Okay. Actually, you know what? We've spent enough time on position. Here's a velocity versus time graph. Now, remembering this formula, because we've only just kind of talked about it, we haven't used it yet. This is how we calculate acceleration. Final velocity minus initial velocity divided by time. You'll notice that sets up to be the slope of a line on this type of graph. Y minus b over x, okay? But for this graph, we don't have a linear fit, right? So if I want to calculate the acceleration between 12 and 14 seconds, do I have enough information on this graph to fill in this formula? I do. Okay, what's my final velocity for part A? In other words, how fast is the object going at time 14 seconds? -6, yes? Okay, so acceleration equals -6 minus, all right, what's VI?
2.
Yep, 2, okay, it's up here. And what's my time?
19. Oh, 2 seconds.
2 seconds. All right, -6 minus 2 is -8 over 2. Okay, so the acceleration during that time is -4 meters per second. Now, if we look at our graph, that's pretty much what the graph is showing. Okay, 12 seconds to 13 seconds. How much did it change its velocity by? 4. -4. Right? It went from 2, +2 to -2. And then it went from -2 to -6. Another 4. Okay? So we're calculating the acceleration during that time. Now, questions?
So what points do you choose? Do you just choose the highest and lowest points, or are there like certain ones?
Well, I picked the ones that it asked for.
Oh, okay.
14 and 12 seconds, right? So 14 was my final, 12 was my initial, right? And then with these two, I was just pointing out that yes, in fact, it does change by
Okay.
-4 meters per second every second, okay? All right, if I was gonna calculate the total displacement over the whole trip, and we won't get this done today, okay? What do I need to do with this graph? It's a velocity versus time graph. Okay. What's my displacement between 0 and 2 seconds? Okay, how do you know that? This graph doesn't show displacement. How do you know it's 0? You're right. Okay, there's no slope, the line's staying flat. But again, this graph, this line isn't showing displacement. This graph is showing velocity. What was the velocity in the first 2 seconds? Okay, if my velocity is 0, can I possibly have any displacement? I cannot. Okay, so my average velocity was 0 times 2 is 0. Okay, took average velocity times time. All right. What's the object doing here? Accelerating negatively. It's also traveling backwards, okay, but it's accelerating negatively. Okay, it's moving in a negative direction. It's also accelerating in a negative direction. If I wanted to calculate the total displacement on this graph, I got to do average velocity times time for every part of the graph where the object is moving. Okay, that means I don't have to do it here because there's nothing to calculate, but I would have to do it here, 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 here. I got a whole bunch of shapes that I have to calculate the area of. Okay, remember, displacement on a velocity versus time graph is the area between the line and the x-axis. So we would be looking at these two triangles here. We'd be looking at those two little triangles and this big rectangle in between them. Probably be looking at that triangle there, that triangle there, that rectangle, and that little triangle. Okay? Everywhere where the object is moving, it will have a displacement. And that displacement is calculated by taking the average velocity, that would be the height, over 2 for a triangle, or just the height for a rectangle, okay, times the base, which is the time. That's what we're going to start out with tomorrow. Okay, I need you guys to clean off those desks so I can spray them down, please. Everybody mask up because I'm now going to be walking around.